In today's video, here is a nice problem of African Mathematics Olympiad year 2004. Here is the following question. Do there exist positive integers m and n satisfied this equation? We have 3 is multiplied by n squared plus 3 times n plus number 7 equals m cubed. Okay? So the meaning of this question, so there is a solution for this equation. Okay? This is the question. So I'm going to solve this equation as we have a solution. Then at some point we cannot find a solution, which is impossible to find a solution for this equation due to the constructions of this equation. Here is a few information that you can use as a tool here. So if we have A divides B, equivalent B is a congruent to 0 mod A. Okay? There exists M such that we have B equals M is multiplied by A, which means B is a multiple of A. Okay? So here is a second tool. We have, if we have A divides BC, implies A divides B or A divides C. Last tool here, for the Fermat-Liouville theorem, if we have a P as a prime, not divides A as an integer, implies A to the P minus 1 is a congruent to 1 mod P. Okay? Now let's go through this one. So we have this following equation. We have 3 is multiplied by n squared plus 3n plus number 7 equals m cubed. Okay? So the best way to factor out this one, I'm going to split this number 7 into 2 terms. I'm going to put it as number 6 plus number 1. Then I'm going to use this number 6 as a common multiplier for these 3 terms here, as we see here, because we have number 3. So if I'm going to put number 6 here, it will be easier to factor out this one. Okay? Then I need number 1, because as you move in number 1 to the right, I will have a nice term which we can use to factor out this term m squared, m cubed minus number 1. Okay? So I will have here 3n squared plus 3n plus number 6 equals m cubed minus number 1, like this. So this one, it's simply going to factor out this on this form, m minus 1 factor m squared plus m plus number 1. Okay? For these terms, I'm going to put number 3 as a common factor. I'm simply going to put parentheses here. This one becomes number 2 here. Okay? Like this. So I will have this expression 3 is multiplied by this term, which is n squared plus 3n plus number 2 equals m minus number 1 factor m squared plus m plus number 1, like this. Okay? Here is a nice thing here. 3 divides left hand side of this equation. Okay? Which means 3 is also going to divide right hand side of this equation. Okay? But we don't know 3 is going to divide m minus 1 or this term. Okay? So which means 3 divides m minus number 1 or 3 divides m squared plus m plus number 1. So as we have here in this tool, I'm going to use the second tool here. We are going to show one of the term is impossible to be divisible by number 3. I'm going to show this term, it's impossible to be divisible by number 3. Okay? So by the way of contradiction, we can put 3 divides this one. At the end of the term, we will find the contradiction. Or there is another nice way we can prove this one. So we are going to consider 3 not divides m minus 1 contradiction. We must conclude 3 must be divided m minus number 1. That's what we are going to do now. So by the way of contradiction, suppose 3 not divides m minus number 1. Okay? We are allowed to apply the Fermat-Liouville theorem, because if we have P, like if we have a prime not divides m minus 1 as an integer, which means m minus 1 to the square is a congruent to 1 mod 3. Okay? So this one is telling us by the Fermat-Liouville theorem, we have m minus number 1 squared, which is p minus 1, is a congruent to 1 mod 3. Okay, like this. Now I have two options. I will have m minus number 1. But I'm going to take this square. I'm going to take the square root on both sides. I get m minus 1 is a congruent to 1 mod 3, or m minus number 1 is a congruent to minus 1 mod 3. As you take in the square root on both sides, you can have positive or negative number. Okay, as you take in the square root on both sides, you can have plus or minus here. Okay, so I'm going to go through each one. So I'm going to start with this one. By taking this number 1 to the left, I get here m minus 2 is a congruent to 0 mod 3. So according to the divisibility statement, I will have 3 divides m minus 2 equivalent. Okay, m minus 2 equals 3 is multiplied by k. What is a k? Is a some natural number. Okay, m equals 3k plus number 2. Okay, I'm going to take this value of m and insert it into the original equation to see what's given us. Okay, I get here 3n squared plus 3n plus number 7 equals 3k plus number 2 cubed. Okay, so what I'm going to do now, I'm going to reduce both sides of this equation to mod 3. So if I'm going to do that, this 3 will be cancelled out. This number 7 becomes 6 plus number 1. This 3k will be 0. And also this 6 will be 0 because 6 is a multiple of 3. Which means I get left hand side of this equation 1 is a congruent to 2 cubed, which is 8. 8 is 2 more than 6, which is a congruent to 2 mod 3. This one is telling us by taking this number 2 to the left, I get 1 minus 2, which is minus number 1 is a congruent to 0 mod 3. Okay, which is impossible. Okay, it's clearly it's a contradiction, which means this case doesn't work. Okay, so let's move on to this case. Now let's check this case. When we have m minus 1 is a congruent to minus 1 mod 3, because this, by applying the Fermat-Leroy theorem, it gives us two cases. It gives us this one is a congruent to 1 or is a congruent to minus 1. The one which has 1 mod 3, it didn't work. Okay, which means we are going to check the second one, which is this one. So what I'm going to do now, I'm simply going to move this minus number 1 to the left. I get here m is a congruent to 0 mod 3, like this. This one is telling us 3 divides m. If 3 divides m, m is a multiple of 3, which means I get m equals 3k. Okay, then I'm going to take this value of m and insert it into the original equation, which means both cases don't work here. Now it's clearly is a contradiction. What we have contradicted? We have contradicted our assumptions, because we have assumed 3 not divides m minus number 1, and we found that contradiction, which means this one exactly 3 divides m minus number 1. Okay, if 3 divides m minus number 1, which means 3 not divides the second one. Okay, now let's clean up this board and move on to the next case. Previously we were arguing about this argument and we came up with these nice results. We found 3 divides m minus number 1. This one is arithmetically is going to tell us 3 not divides the second term, which is m squared plus m plus number 1. We are going to take the advantage of this one and make these two statements together and to see what's given us. Okay, so 3 divides m minus number 1, it's clearly which means m minus number 1 equals 3 is multiplied by k. Where is a k? Is a some natural number. 3 not divides this term, which means we are going to apply the Fermat-Liouville theorem, because we have the 3 as a prime, not divides this integer, which means I will have m square plus m plus number 1 square, which is p minus number 1, 3 minus 1, is a congruent to 1 mod 3. Okay, here is also I will have two cases. Okay, so the first I will have m square plus m plus number 1 is a congruent to 1 mod 3, or m square plus m plus number 1 is a congruent to minus 1 mod 3, because I get a real of the square root by taking the square root on both sides, then it's giving us this plus or minus 1. Okay, so I have to go through each case. So I'm going to start with this case. Now I'm going to start cancelling number 1 from the left and the right, and then I'm going to take m as a common factor here. I get m is multiplied by m plus number 1 is a congruent to 0 mod 3. Okay, also I have two cases here. This one is telling us 3 divides m, or 3 divides m plus number 1. Okay, 3 divides m, it doesn't work, because we already proved 3 divides m minus number 1, which means 3 cannot divide m due to this one, because if 3 as a prime divides m minus number 1, this one is arithmetically it cannot divide m. So this one is going to be ruled out of this possibility. Let's move on to the second one. Also I will have the same thing here. Since 3 not divides m minus number 1, also 3 cannot divide m plus number 1 here. Okay, GCD of m minus number 1 and m plus number 1 equals either 1 or 2. Okay, if they are odd, they will become odd consecutive integers, which means that GCD equals 1. Since 3 divides m minus number 1, which means 3 cannot divide m plus number 1, so also this one doesn't work. So let's move on to the second case. Now we are going to go through this case. So if this one doesn't work, which means this one is going to work. Okay, so I'm going to take this one. I will have m square plus m plus number 1. I'm going to move over this minus 1 to the left, becomes number 2 here, is a congruent to 0 mod 3. Okay, so what I'm going to do now, I'm going to use this fact. We have m minus 1 equals 3k, which means I get m equals 3k plus number 1 by taking this number 1 to the right. Then I'm going to take this value of m and insert it into this equation here. So I get here m will be replaced with 3k plus number 1 square plus 3k plus number 1 plus number 2 is a congruent to 0 mod 3. Okay, since I'm working on mod 3, so I'm going to cancel number 3 here. This one is 0, this one is 0. Okay, so which means I will have 1 plus 1 plus 2, which means I will have 4 is a congruent to 0 mod 3. This one is telling us 3 divides number 4, which is clearly it's a contradiction. It's impossible. Okay, which means we have no solution for this equation. Now we have answered our question. So if you have any question regarding this problem, just put it in the comment section below. By the way, don't forget to support us with a like and subscribe. Thank you for watching. I will see you next video. Bye.